Today on Applied Science, I'd like to show you this project that I've been working on. This is a bite sensor for a computer-human interface. So you might want this for a lot of different reasons, but this particular one was built for a musician who doesn't have the use of his legs, but still needs to control the sustain pedal for his digital piano. So in this video, it's going to be a mix of different construction techniques, 3D printing, rapid prototyping, and a little bit of design philosophy. I thought I had a perfect solution, and it turned out to have pretty big problems. And so this philosophy of build first and ask questions later, I think is especially apparent here. Also, I apologize for the lack of videos recently. This is due in part to my shop being burglarized on Christmas night. And the burglar found so much good stuff, he actually stole my wheelbarrow and loaded it up with all my stuff and carted the whole thing off while I was sleeping. Strangely and thankfully, he didn't steal anything super expensive or difficult to replace, mostly just hand tools and power tools. And my homeowner's insurance policy has been very helpful, and we're almost back up to full capacity, but a little bit of a bump in the road there. The story of this project began when a musician contacted me and showed me his existing setup for controlling his piano. And that was literally just a micro switch like this that he would bite on to control the sustain function, the sustain pedal of his digital piano. And I can see why this would be very annoying. I mean, it's basically just on-off control, and modern high-quality digital pianos allow the pedal to be continuously controlled. So stepping on it halfway gives you a different effect, or whether you step on it quickly or slowly gives you a lot more expressiveness and dimensionality in playing, and I could see that being a pretty important part of this. So the challenge here, this whole project, is to make a continuous pedal, something that's linear and has a continuous output, and it has to be compatible with the Roland digital piano. Now, we don't know what's inside the piano as far as circuitry goes. All we know is that there's a 3-pin connection, and so I bought one of these pedals and took it apart, and sure enough, there's just a potentiometer in there. It's a 10K pot, and it's wired up to the 3 terminals here. There's no active circuitry in this pedal. However, if we wanted to build something that was active and electrically connected to the digital piano, we would have to know a lot more about what's going on circuitry-wise. We don't know if they're using an AD converter that's 5 volts or 3.3 volts, or maybe it's an RC oscillator and they measure the frequency. We just don't know. And so any sort of solution we come up with is going to probably have to be passive, just a potentiometer, because any sort of digital circuitry introduced has a pretty high likelihood of not working with the piano. And you might be thinking, well, we could use one of those digital potentiometer chips. Sure, but those still require a voltage rail reference. You can't have a floating, it's not like you have a floating voltage that you can just control. One possible solution would be to get a potentiometer and control it with a servo. That's a good way to get some isolation. And in certain cases that could work, but it's just not really that elegant. So, you know, I was thinking along the lines, the easiest way to build a force sensor that you would bite on would be to use a flexi-force sensor like this. And this is great because they're so thin and small that you could put this in almost any kind of 3D printed case of any shape. And when you bite on this, we could electrically convey that out to the piano. But like I say, it's because of all these unknowns around the electrical system. There's a big problem. And as we'll see later, this also has a physical problem. When you bite on this, there's no physical response. And even if we added a spring or a foam cushion to this, biting on it provides very, very little physical feedback. And this is actually a crucial part of this whole process. Remember, the point of this whole exercise is to make a very expressive, linear, very consistent controller. And so if it has a crappy sort of response to it, if it doesn't feel like you're really controlling something physical like a pedal, then it's not going to work. It's not a good solution. When starting this, I didn't realize how crucial the physical feedback of this controller was going to be, and so I thought I had a super perfect solution, and here it is. I was going pneumatic, and I thought this was great because it ticks every box in the list of requirements we might come up with for this project. So for example, there's no electronics in the mouth whatsoever, so it's kind of inherently safe. We can mold this silicone pad, which I'll show later in the video, to be any shape we want, any thickness, any height, both sides of the mouth, one side of the mouth, anything. It can even be easily replaceable. You can cut the hose and put a splice in it and so on. So I built this first and tested it out and realized there was one problem right off the bat. I'm using this clippered commercial cylinder here. So when I squeeze this, you know, it extends the thing. Obviously, you can see one problem, it doesn't return automatically. Well, that's easy enough, we could add a spring. But another problem is that there's stiction in here. There's an O-ring that seals it, and let me try to push this to the midpoint of its travel. So I'm adding more and more force very, very slowly. And then suddenly it just jerks out like that. You saw that? There's no way to control this smoothly because of the stiction problem here. And eventually what would happen is we would take a potentiometer with a linkage or something and connect it up like this. And this whole part would reside in a box that's down on the table, and there would be this super flexible, lightweight link that would go up to the mouth. And so this is great because it's just so easy and lightweight and small. It just seems so elegant. And I thought, well, we can solve these other problems. Like I say, the spring, the stiction. Here's a really good solution to the stiction problem. Use a bellows or an accordion like this. And then when we squeeze on this, there is no stiction because there are no moving parts. There's no friction. There's no sliding friction in here. So if we were to connect this accordion bellows up to a linkage and then up to a potentiometer like this, when we squeeze this, now stiction is not a problem. So we've solved that one. I mean, there'll be a little bit of stiction in the pot, but we can find one of those that's a very low drag. So this would actually work. But again, the problem that I didn't anticipate was that there's just no feedback from this. This is like squeezing a balloon. I mean, it's exactly like squeezing a balloon. And imagine if the accelerator pedal in your car was basically just an air-filled balloon. You could still drive. I mean, you could still control the vehicle, but it's very, very hard to tell what's going on. Like, you can't tell if the pedal is all the way up or all the way down. There's just no way mentally you could say, okay, I'm going to go to half pedal right now. It's just, there's no feedback. There's no physical feedback. So what I realized early on in the project was this thing that we're building is going to have to be physical. There's no way that a spring and a force sensor or a pneumatic control is going to work. Now, you might be thinking, well, that's because I used a compressible fluid. There's just air in here. If I were to put water in here, it would be non-compressible, and then it would have perfect one-to-one control over this thing here. Yeah, to some extent that's true. There's a couple problems though. Keep in mind that if you take a silicone hose like this and fill it with water and cap it off and seal it and leave it for a month, it will actually be empty when you come back. Surprising, but silicone is super permeable to water, and it will not work just with plain water in there. So alternatively, you could use oil or something like that. But now it's not looking so elegant, because if this thing is oil filled and you bite on it and it punctures and sprays oil out everywhere, that's not going to be such a good outcome. And it's just kind of messy. I mean, you can imagine there's going to be leaks, and filling it up is a problem in all this. And even with a non-compressible fluid in here, the silicone itself is quite rubbery and springy, and so is this whole hose. And so trying to make this into a workable solution is not so good. Another thing I didn't anticipate is that the force transfer is not nearly as good as I thought. Like, there's a lot of wasted force in this system. So when you bite down here, you don't actually end up with that much actuation force out here. And I've played with the areas and the ratios of all this, and it's just not that good. It's actually right on the cusp of being acceptable, where maybe there's 5 millimeters of travel, 5 millimeters of bite travel here, for example, and it's just barely enough to get out enough travel out here. So after playing with that for a while, I was thinking that maybe my perfect solution of pneumatic or hydraulic control is not all it's cracked up to be. Probably time for a new prototype. So, coming back to this design philosophy, this really did tick all of the boxes that I thought I had. Waterproof, lightweight, could be made into any shape. It's easily replaceable. It's easily repairable. It's extensible. I mean, all these things. It ticks every box that I thought I had. But the one box that's critical, and that's this physical response, I didn't even know was a requirement up front. It's something that I only uncovered through building this and trying it myself. And so the point is, just building and trying is actually faster than trying to estimate what it is you want to achieve. So anyway, so we'll put that aside, and this was design number 2. So in this design, I knew I wanted to have a physical linkage, due to the problems with hydraulic or pneumatic systems. And so this one is built very mechanically. And the idea here is that your lips could seal at this point here. So this part goes inside the mouth, and then this part is outside the mouth. And one of the benefits with this is that you can build it with just simple tools and an FDM 3D printer. And so at one point I was thinking, wouldn't it be nice to have like an open source design that anyone could build? And even additionally, the potentiometer here is actually the same potentiometer that came out of the original Roland pedal. So if you were to buy this pedal and then use a 3D printed part, you could completely build one of these things on your own. And I thought that was an attractive design part. Another interesting thing is that this potentiometer has a very, very short travel. So it completes 10 k ohms of travel in just about 45 degrees of rotation, which is very small for a potentiometer. Most pots are 320 degrees, and it's possible to find some that are like 130 degrees, but finding the ones that are 45 degrees is pretty rare. I think they're typically specially made for manufacturers to build things like this. But anyway, I really liked the response. It has a really nice, controllable, consistent response, and the linkages here are set up such that it's pretty darn linear. I was also very surprised at how strong these pinned joints were. So the way I made this was to 3D print a pilot hole and then drill it out with a drill so that it's exactly the right diameter, and then just pressed in a brass rod and cut the rod off flush at the end and then used a drop of glue to hold it there. And this is actually surprisingly good. You can bite on this and it's not weak. I mean, it actually stands up and it's better than I thought. You can see though that there is a little bit of bite damage going on here, so it's not the strongest thing ever, but this was not bad. And then of course, to make this waterproof, I made a silicone mold, and like I say, I'll show you the details of this in just a minute, of how to make these custom form-fit silicone molds. I haven't glued it shut yet, but this is, I would seal the seam up. And this was kind of okay. The idea is, again, you'd seal your lips around here, so this part would be inside the mouth and this part would be outside. And it's okay. It's not bad. It's the silicone overmolding causes a little bit of difficulty in crushing this. Another problem I discovered is that the silicone, this is cast. I cast this silicone out of Smooth-On. Sorta clear 40. The 40 means 40A durometer, which is fairly soft stuff. And as it turns out, when you bite on this, the area of silicone between a tooth and the hard PLA plastic is enough where the plastic is punctured. And so if you look in here, it's got a bunch of teeth marks that go right through. And biting on this was actually pretty unpleasant because you could feel the plastic yielding under tooth pressure. Like you would bite down and then you'd feel kind of crunchy as it was going through the silicone. So anyway, so this, I learned quite a bit with this one. It's not going to be sufficient to have just silicone providing a surface for the teeth to bear against. And then also, even though this is, it's an okay mechanism, it's not bad, it still could be improved a bit. I mean, it's obviously huge and chunky and everything. And I think giving up the ability to 3D print this on any 3D printer in exchange for a better mechanism would be a good benefit. So let's move on to the design number 3. For the following designs, I realized that if I was going to use the original potentiometer from this pedal, this 45-degree rotating potentiometer, the device was going to be too large to fit inside the mouth wholly. Like basically there's always going to be something sticking out of the mouth because this pot is just too big. And so I started thinking, well, I need to find a 10K potentiometer that has a tiny amount of travel that's also small enough to fit inside the mouth. So I searched around on DigiKey and found something that I didn't know existed. There's these little tiny linear potentiometers, and this, you can order these in different travels. The physical travel is always about 12 millimeters, but the electrical travel can be as low as like 3.5 millimeters. I think they make 3, 6, and 12. And the whole thing is very small. It's even got wires that come out that are permanently bonded. And this seemed like one of the smallest travel and also smallest physical potentiometers that you can get anywhere. This would be small enough to build into a device that fits inside the mouth and so on. So after I found these, I thought, well, I know a good idea. I'll make like a living hinge type device and put the pot in the middle. And then when you bite on this, the living hinge expands and these inner parts become further away, and I'll just connect the pot up like this, and it's nice and elegant because when you bite down fully on it, it becomes solid. And so it's as compact as it can be vertically. And you know, the challenge with this is that's the material properties. I mean, PLA 3D printed, it doesn't make good living hinges at all. This thing is pretty terrible. So that didn't go anywhere. So here's the overall winning design. I really like the button response of this. You can press it sort of anywhere, it doesn't jam. It has a really nice, consistent, linear feel, good feedback, no spring crunchiness to it. It's very smooth and consistent. And you can even take it apart and see what's in here. So we've got that linear pot again. I'll put links to all this stuff, of course, in the description. And the mechanism is just a ramp. So I've basically got a whole bunch of teeth like this that interface with little nubs sticking out of the top. So when this moves up and down, the ramp just moves this way, and the ramp is connected to that linear pot. And there's only one spring in there. It's actually a ballpoint pen spring, and that's what provides the force going this way, and it translates back into the button press. So things always look very simple. Looking at it now, you say, well, yeah, it was just a ramp. I mean, it couldn't be a more simple mechanism. But the process of getting here can often be complex, and starting off with a pneumatic solution like this, it ends up looking very different. And it's only because of these design requirements that were not known from the beginning of having this really very definite. I can tell exactly when the pedal is all the way up or down. You can instantly go halfway without thinking about it. It's very easy to go 3/4 way, all this kind of thing. It has about the same amount of force all the way up and down the travel. It has a lot of user interface aspects to it that are far, far better than this, even though from an engineering point of view, this is almost more elegant and impressive in some ways. I haven't glued the top of this on yet. I solved the problem of teeth biting through my cast silicone by using a little strip of this high temperature fabric reinforced silicone. This is really tough stuff, and I cast the custom part of this in the soft 40A, and then had a little cutout in here and glued in this reinforced silicone, top and bottom. And so when I get this thing ready to send off to the user, I'll add more sealant around here, and then this thing will be airtight and provide keep basically the halves from coming apart there. Let's talk about some construction tips and tricks that I use to create these prototypes. First of all, how to make a custom shaped silicone enclosure like this that's airtight. In CAD, I use Fusion 360. The first thing to do is to draw a chunky block shape around the part that you want to encapsulate, and then subtract that chunky block shape from another block. And basically what we're going to do is come up with 2 molds, and each mold will have 2 pieces. So a top and a bottom, and you can decide where you want to have a split line there based on your part geometry. And so I printed these out on a PLA printer at very low infill. It's just, this thing weighs almost nothing. And the trick is, so these 2 pieces go together, of course. You got the top and bottom molds here. And I use Smooth-On products because it's easy to buy these in small quantities. And like I say, this is 40A durometer. Smooth-On has about 100 different kinds of castable silicone. So you have a lot of options there. But the idea is mix up the silicone as according to directions. It helps to degas it in a vacuum chamber, and then pour it in here and close the mold up. It'll squeeze out all over the place. That's okay. And then just put a light clamp on this thing and wait for a day. Open it up, and you've got your part. Pop the part out like that. You typically don't even have to use mold release, although it's helpful to give it a quick little spray. It doesn't make a huge difference. Next question, how to seal these together to make an airtight enclosure. There's a special glue out there called Silpoxy, and this stuff is truly magic. I have not found a glue that works like this in any form. This is really magic stuff. And what I do is pull the back out of a syringe and fill it up with this, and then put a small tip on the end and put a bead around just like that, and then put the 2 halves together, and again wait about a day to be sure, and these parts will be absolutely bonded together. This provides a bond that is almost as strong as the base material, and it will be airtight. Pretty amazing stuff. Since this final design involved quite a lot of sliding surfaces, I mean, it's basically a bunch of ramps that just slide against each other, the choice of lubricant was also a pretty critical element, because we wanted this thing to be silky smooth, again, because it has to be a successful product. So I tried a few different lubricants and was surprised at how these actually didn't work that well. I also tried some silicone vacuum grease, which isn't here at the moment, and it worked okay, but I was looking for something a little bit more lubricious, and thought this would be great because it's so thin. This is almost a liquid. This turned out to be terrible, actually. It was worse than nothing at all. And the plastic that I'm using is the durable resin from Form Labs. These are all Form Labs 3D printed parts. And the durable resin is similar to polypropylene. It has much more fracture toughness than their other resins. And even though it's not quite as stiff as some of the other ones, the fact that it doesn't chip and crack under a lot of stress is quite useful in this application. I tried it with the standard clear resin, and even though it is more rigid, I couldn't even assemble it without cracking pieces off, whereas the durable it seems plenty strong. It's fine. But anyway, getting back to the lubricant, I also tried my favorite Lubricante Superior, and this also failed me. I was surprised. Again, not very lubricious with this plastic, but the super white lithium grease turned out to be a winner. This was by far and away the best choice. It's thick, and so it doesn't get displaced, and it's very smooth, and it provides exactly the kind of feel that I was looking for. Let's talk about the cable strain relief, since that's another common point of failure in these devices and something that's worth worrying about when you're designing these. So I ended up using a shielded cable, not because I really needed the shield, but because the shield provides a good way to anchor the cable in here. This part is so small that we can't really use a screw or a cable tie or really anything to do a good strain relief. So what I ended up doing was using the cable braid itself. It's a nice braid. It's not just a foil shield, it's a braided shield. And I glued the braid to the plastic here with a very tenacious glue. And so when you yank on this, all the force goes through the cable braid and into the housing, as opposed to putting stress on the electrical connections. It's not ideal, but it's not terrible either. And the choice of glue is important, and I like to use these light cure adhesives. When using a 3D printed resin from a resin printer, the light cure adhesive makes an incredibly good bond. Again, it's almost as strong as the base material. So what I do is take this 3311, which is my favorite variety of this, and load up a little syringe, and so you can very accurately dispense, a drop of glue right where you need it, and then come in with a 405 laser pointer and just hit that with the 405 laser pointer, which is also dead. There we go. Cures it in seconds. I mean, really about 20 or 30 seconds, and that thing is good to go. I think it's possible that will be a failure point, but hopefully not. It's a pretty good strong bond there. These little potentiometers had another problem. They're actually built too well. In fact, they have O-rings in here to seal the entire thing, and the bottom is, glued shut. There's no way to get in there. So this one I actually cut the top open so we could see what was, going on inside there. And the problem with these O-rings is that the stiction and friction that they contribute to the system was too much. And so in our final product here, with those O-rings in place, this thing would not operate smoothly because we just don't have that much overhead. I mean, this thing has to be much looser for the thing to work properly. So I had to get those O-rings out without ruining the device, which was also an interesting challenge. For this one, I beat on the shaft enough and actually was able to push this thing out. You can see it has a stop internally so that you can't get it out all the way, but if you hit it with a hammer, it will come out. And I was able to remove the little bushings that are on the end and then pull the O-rings out, but that kind of ruins the bushings and anything. So I found out what I could do after taking one apart and noticing where the O-rings were inside there is to drill a tiny little hole right where I knew where the O-ring gland was, and then go in there with a pick, a dental pick, and sort of laparoscopically extract that O-ring through the hole in the top without hurting the bearings or anything else in there. And now the thing operates, nice and smoothly, without any stiction or friction from the O-rings inside that potentiometer. Of course, it's not hermetically sealed anymore, but we don't care because this whole thing is going to be sealed with our own silicone enclosure. I also found this kind of linear potentiometer on DigiKey, which I didn't know existed. It's spring-loaded, and it's a little too big for this project, but it's really nice in that the resistance starts changing the instant something starts touching the outside here. So you can use it as a really accurate sort of like end travel sensor for maybe a linear motion device or something. If you need to return to it in exact position each time, it's pretty useful. So anyway, I hope that was an interesting look at the design process, and maybe you picked up some useful tips and tricks and tools along the way. So I'm going to sil-epoxy the top of this thing back on here, and then cut the cord at some convenient length and put the original cable connector on the end, and package this up and send it off to its new owner. So hopefully he enjoys using it as much as I enjoyed designing and building it, and hope you found that interesting, and I will see you next time. Bye.